So first thing I'm going to notice here is that I have an interval with a radical. So I'm going to want to use trig sub. So I'm going to start drawing my triangle. A little more space there. Some angle of theta. And I want to think about what trig identities I can use to look like this. First thing that comes to mind for me is I know tan squared theta plus 1 is equal to secant squared theta. So I can subtract 1 from both sides. Say that tan squared theta is equal to secant squared theta minus 1. So I've got this in this form. But I don't have a 1, I have a 2. So what I want to do is I want to say that I want to find the square root of this constant. Say that a is equal to the square root 2. And multiply everything in my equation by a squared. So I know that a squared tan squared theta is equal to a squared secant squared theta minus a squared. And then I can simplify this all out to a tan theta squared is equal to a secant theta squared minus a squared. So I want to substitute something here for x. And the pretty clear thing is my a secant theta. Because if a secant theta is equal to x, then this whole thing will look like the radical I have. So if I say x is equal to a secant theta, I'm going to box that because that is one of the truths I'm operating under now. And then I know a secant theta, or rather, I know secant theta is my hypotenuse over my adjacent. So for this to be true, that must mean that my adjacent side is equal to a, my hypotenuse is equal to x. And I can then verify secant theta is equal to x over a. I can multiply by a, and I can see a secant theta is equal to x. So that's holding true so far. And then that would mean, by the Pythagorean theorem, that this side would be equal to the square root of my hypotenuse squared minus my adjacent squared. That looks exactly like the radical I'm trying to replace. So I'm on the right track still.
Mm-hmm.
Now from here, there's two ways you can go about this, depending on really what you remember. You can either go ahead and make your substitution for x, and then see what you can do here. Or I can look at my triangle and see that I have the radical I want, and think about what function I can use to get that radical.
Because we have the radical as the opposite side, and we can do that over the adjacent side to get tan.
Yep. So knowing that tan is my opposite over my adjacent, then I know from this triangle tan theta is equal to square roots x squared minus a squared, which is 2, over my adjacent, which is a. And then if I want that radical just by itself, I just got to multiply by a.
A tan theta.
So at this point, I can swap this whole thing for a tan theta. But the other method I can do is I can plug in a secant theta into my x.
But that is hardcore.
Yeah, and again, we've declared x is equal to a secant theta, so when we're making the substitution, we have to make it not just in the radical, but outside of the radical as well.
Sorry to interrupt, but so is x always, like in this case, the hypotenuse? I just don't get how you knew what side of the triangle everything was.
So what you're gonna
I've been struggling with this.
do is you're gonna see that you have a radical of the form. I put that. Square root plus or minus a squared plus or minus x squared, right?
Mm-hmm.
And I'm going to know that that's pretty similar to the Pythagorean theorem, right? Where I have a squared plus b squared equals c squared, or square root of a squared plus b squared equals c. So if I can figure out what to use for c, I can replace this with something much more easy to use, right?
Yeah.
And really, actually, now I think about it, you could probably just go right there. Say that a squared b squared equals c squared. And if in this case I have the square root of constant minus x, then I would want to subtract one of these. It could be either from c squared. So I can have a positive number is equal to something minus something. And then I can see if I just substitute a into c, smaller triangle here. And specifically, this would have to be squared for this to work. Or actually, it don't have to be squared. We could say if this wasn't squared, that this side is actually the square root of whatever I had. Right? And for b, square root.
I still don't get how you knew what side to put it on. I don't know why I don't get it. I know you've gone over it a billion times.
So if I see this radical, which is not only is it very similar to the Pythagorean theorem, but it's also the formula for a circle, because the unit circle defines all these triangles.
Mm-hmm.
So I have a radical plus or minus a constant plus or minus x squared, or really any function can be this x. I'm going to go back to our Pythagorean theorem, and I'm going to ask myself, what can I do to make this look like that?
Like the way that I think about it is you see in the first one here, it's a squared plus x squared, right? And that's like a squared plus b squared equals c squared. Because like if you have a squared plus x squared equals c squared, if you want to get c by itself, you'd square root that whole thing and get a squared plus x squared. So you know that this is the combination of a and b, which is c, right? So you know that the whole rational is c. But then for this one, you have the bigger side minus a smaller side squared, because these are all squared, like a would be squared here, like invisibly. But you know, this is the big one, so it's going to be a is the hypotenuse, because it's the big one minus a small one, right? Because we want it to be positive. And then here you got the big one minus the small one. So this is going to be the hypotenuse is 4.
Okay,
Right.
thanks.
So if I see that I have a constant minus an unknown, I can remake that here by thinking about how do I make this look like any of these minus any of the others. So for that to work, I would have to do, say, minus b squared. We're subtracting b squared from both sides. And so for this, then I want to equal something simple, which will be a squared. So for this to equal a squared, that must mean that the square root of our a here, or if it was a squared, square root of a has to be on the hypotenuse, and that x has to be the adjacent, which means that a is my whole thing here. Square root a squared minus x squared. And let's make this small. Got some space. And so if I had square root x squared minus a squared, I would start making my triangle. Sides C, B, and A. And then a squared plus b squared c squared. And so to make this look like that, I need to subtract one of these, and I'm just going to choose b squared. And so that must mean that x is c, that a is b, and that the whole thing is this a. And using this method, yeah, and so this method's going to end up a little different depending on what you subtract with to what trig identities you're going to end up with. Because doing this, I chose to subtract the opposite side, which means that I would want x over a, hypotenuse over opposite to equal x over b, or x over a, so that I can do a times some function. And in that case, I would want to use cosecant theta is equal to x, since cosecant theta be equal to x over
I
a.
have another question. Is that okay?
Good.
Um, so like C equals X, but never mind. It's all good. I don't know how to phrase it. I'm sorry. I don't want to take up anyone's time.
Yeah, and I'll say again, the Professor Leonard videos for, what was it, 7.3 is what he has it
Dot
as.
3. Yeah,
Yeah,
that
is
was really helpful. But also, like, I mean, I don't care if you like keep asking questions personally.
I just don't want anyone to have to go over the same thing over and over. I watched over an hour of the Professor Leonard video that you guys are talking about. It was really helpful, but so I'll just watch the last hour later. But yeah, I
Wait,
don't
but
want
the
to
one did you watch the
question.
like 2 hour long one?
Yeah, I've watched pretty much
That
every
was like,
Professor Leonard lecture for all of
oh,
this,
okay.
like this whole class.
Okay. Because the 7.3 one was like 44 minutes long.
Maybe I was talking maybe the 7.2 one, but I know I watched like two 2-hour lectures
Okay.
in it. not fun. And one was integration by part, and then the other was this trig stuff. And he had like 7.2 and 7.3. But I didn't finish 7.3, so I might not know how long it was, but I didn't finish it. But yeah, I
Okay.
don't want to take up anyone's time, so I'll go try to find a video on this because I just can't keep up. So
Let's go back to the practice problem we're working there. So we're substituting a secant theta into x. We're substituting a as square root 2. That's a squared. And so from this, we already found earlier that a squared theta squared, a secant theta squared minus a squared is equal to a tan theta squared. And so we find the square root, get rid of that squared, is another way of finding that a radical is equal to a tan
Like if
theta.
you just and then if you just like factor out the a under the radical, then you can just use that secant squared minus 1 to find the substitution of the tangent.
But the key thing here also is that we can't really factor out our a because we need our a in here to be equal to this tan theta. Or actually no, you're right. We could do that as well. We could factor out.
Just to get it to be minus 1, I guess.
We would have the square root a squared times secant.
Because then it just
squared
seems clear to me
theta.
that it's secant squared theta minus 1.
Yeah. And you can factor out this a, and you'd be left with the square root secant squared theta minus 1 times a. Yeah,
And then it would be, and then you put in the tan a, so it's like 8 tan a again.
Yep, and there's just a lot of ways to approach this and just come at the same, to find the same solution for all these problems.
Yeah, I feel like I just like the finding it substitution with the triangle right away because sometimes the algebra with the other way just kind of like with replacing x everywhere just kind of gets me tripped up.
Yeah, the very first thing you're always going to want to do is just make a triangle. Even if you're doing it algebraically, by making any statement where you can substitute a trig function in for x, you have defined a triangle of some angle theta relative to x. If that makes sense.
So is in the lost folklore of Atlantis, does Zella mean math god?
That's just my name backwards.
Oh, Alex. Alex.
So
Oh, cool. Zella.
even if we didn't have this triangle written out, we said x is equal to a secant theta, which means the triangle exists. That's a consequence of this statement. And so we can refine the triangle if we have something we want to come find later, or we can just keep going and see if we need it. And so, again, we'll replace our radical here for a tan theta. And then dx. So we have a variable theta, but our integration variable is dx. So we need
So
to
now we
find.
can find dx because we defined x as being a secant theta. So we can find the dx of it.
So if I find the differential, both sides, what would I have?
A tan theta. Oh wait, no. A secant theta tan theta. A secant theta tan theta.
And so what would be on this side?
Dx equals a secant theta tan theta.
And what rule would I use to find this? Because I have another variable here.
So we have to do d theta at the end because it's like in terms of another thing, implicit or something.
Yeah, so we're using a differential, which is like implicit differentiation, except we're doing it in terms of nothing. So we're finding it relative to nothing. That's, yeah, mathematicians don't like it. Tan theta, d theta. Another way you can look at it is if we did it relative to x, if we found the derivative of x relative to x, that would just be 1. And if we find the derivative of this side relative to x, so d over dx, a secant theta, we would use chain rule, pull the a out first, and use chain rule, so evaluate secant theta as secant theta, tan theta, and then we'd be left with the derivative of theta relative to x, d theta over dx, and dx is what we're looking for, so we can multiply both sides by dx.
Hell yeah.
Same conclusion. And so what we're doing, we're taking the differential, is the same thing, we're just skipping that step of taking it all relative to something and multiplying it out.
Like we're just assuming that.
Yep. And that'll become useful when you get to differential equations with partial derivatives.
Okay.
So I can replace dx for this. So then I have, I'm going to move 5 out just to make this radical,
Yeah.
or this fractional be
We
easier
have
to
1
deal with.
over.
So I have 1 over, and then I'm placing dx. So I'm basically multiplying by this in place of multiplying by dx. So I have a secant theta, tan theta, all over, bringing these back down, a secant theta over a tan theta, and then
When
bring
we
it over
can,
there.
we can cancel the a tan thetas and have only secant cubed theta on the bottom.
Yep. And so this will be equal to 5. What else can we do here to make it simple?
Integral of 1 over secant cubed theta d theta. Oh, we can also change it to cosine.
Yep. So the secant theta gets rid of one of these. This tan theta cancels out here. And this a cancels out here. But to remove this 4, or to decrease this exponent on the bottom for secant theta, we have to bring out a first. So we'll have a to the 4 times secant theta. Does that make sense?
Yeah, because we distributed out the power 4.
We know a is a constant, so we can actually just bring it out here as well.
And we could at this point maybe just make it the square root of 2 to the power of 4, which would be equal to 4.
But I get a feeling a might come back in a second, so let's hold off on that till we're at the end. And so, like you said, secant theta is 1 over cosine theta. So 1 over secant theta is cosine theta. So we have 5 over a to the 4 integral cosine theta to the 3 d theta. Just much easier to evaluate just using u substitution.
Cosine squared theta times cosine theta d theta.
So what's the substitution you want to make there?
1 minus sine squared theta.
And what am I going to say is equal to u?
So u is going to be cosine squared. Wait. Yeah, cosine squared theta equals u. Or sine theta equals u. And then du is cosine theta. So now
Again,
sine theta d theta is du.
and again, this is my truth. This is the founding. I'm saying u is a thing that exists, and I'm saying it exists as sine theta. This is like the rock of u. Like u exists with this. This is one of my truths to make you exist. So I want to keep that in mind. And du will be cosine theta d theta. So I want to make these substitutions. I get
1 minus u squared du.
that one. Should be very easy to evaluate now.
Now we have the integral of 1, which is going to be, I think it's theta.
And so what are we taking this integral relative to? What's our integration variable?
Wait, it's u. I messed this up before too. It's u.
So we'll have u minus
Minus 1/3 u cubed.
u cubed over 3. And then
Let's see. And now we sine theta those u's.
yep. So now we got to figure out what this is in terms of x. So put sine theta into all these u's.
Our triangle. Our handy dandy triangle.
4 sine theta times sine cubed theta over 3.
And then
See it?
sine is equal to opposite over hypotenuse. So root of x squared minus 2 over x.
Yep. This is why earlier you want to make this triangle, even though it's not necessary for all of the steps we've done so far. When we get to here, and if we have a trig function that we didn't already define, we'll want this triangle to define it.
Mm-hmm.
So what would sine be from this triangle?
X squared minus 2 over x.
Yep. And again, we defined a as square root 2. So we're going to be using that here. So 5 for a to the 4 times the square root x squared plus a squared for x minus square root x squared as a squared for x cubed.
All cubed.
Cube here.
And then times 1/3
Over 3
plus c.
And then I would start plugging in my a squared.
Mm-hmm.
So
we just replace that all with square root of 2.
5 over 4. Okay.
X squared minus 2 over x.
Yep. 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 Yeah, so we had cosine theta cubed, and with an odd power, we're able to split it into the Pythagorean
Because this is
identity,
the
1 minus square
power
theta,
trig function integration.
and then by saying u is sine theta, we have a cosine theta to help turn into du.
I have a request.
We got
Wait, are you leaving soon?
yes.
Okay. Well, maybe we can do this like some other time then.